Hello, today I will be presenting my work on using deep networks for biomechanical simulation of brain atrophy in healthy aging and dementia. Alzheimer's disease is a neurodegenerative condition which manifests on structural MRI images as progressive tissue loss or atrophy. Cross-sectionally, the progression of disease is well documented and presents with disproportionate atrophy of certain areas of the brain, including the hippocampus and regions of the cortex, relative to age-matched controls. However, disease progression is heterogeneous across individuals and challenging to diagnose from structural MRI alone. Biomechanical models present an alternate avenue to post-hoc classification of Alzheimer's disease from imaging data, and allow instead to build forward models of disease, simulating different possible scenarios for progression. Such models have been used broadly throughout the literature to simulate both atrophy and growth, and are usually based on hyperelastic strain models implemented using finite element methods or finite difference methods. In this project, we propose a novel deep network for biomechanical simulation of brain atrophy. We train a hyperelastic strain model of brain growth and atrophy while building an explicit simulation of atrophy for different populations and time windows. Our model, therefore, parallels a growing body of deep generative interpretable models of disease. But in this work, we take a more explicit approach to explainable and causal modeling by having a model that allows interventions to simulate projections of brain atrophy following differing diagnoses. Our model is composed of two networks. The biomechanical model, highlighted here in yellow, learns to estimate a deformation field from a prescribed atrophy map, corresponding to local volume changes. In turn, the atrophy estimator predicts what these region-wise atrophy values are from certain demographic data and time interval. In this work, we trained the two networks in different stages, which I will explain in more detail in a few slides. At inference time, the model estimates an atrophy map from the metadata, followed by the corresponding displacement field. And a follow-up scan is then computed by applying this displacement field to the corresponding baseline image. The data in this study were obtained from the Alzheimer's Disease Neuroimaging Initiative database. For each subject, we used two different T1-weighted scans, separated by at least 1 year. The dataset includes 4 classes: subjects diagnosed with Alzheimer's disease, subjects with mild cognitive impairments, subjects with significant memory loss, and finally, cognitively normal subjects. In addition to brain-extracted T1 images, we use segmentations and parcellations of the tissues. We use these parcellations to compute true region-wise atrophy maps for each subject. To do this, we simply take the ratio of the volumes for each region between the two time points. So just as an example, if we had a region that's shrinking to half the size of the baseline in the second time point, the corresponding atrophy value between the time points would be 2. Our biomechanical models takes an atrophy map as input to the model in form of a single scalar for each voxel of the brain. A U-net is then used to estimate the displacement field U from the prescribed atrophy. In training, we optimize the network parameters based on a biomechanics-inspired cost function. For this, we follow the convention used in modeling growth of biological tissues and decompose the total deformation gradient into applied growth and elastic deformation, where G is given by the input atrophy map and assumes isotopic growth. We model the brain as a neo-Hookean material and estimate a displacement field that minimizes the strain energy density, considering different tissue characteristics for the brain and the CSF. Then, to further enforce biologically meaningful deformations, we add a last term to encourage zero displacement outside of the skull. Now, to train this model, we use the computed true atrophy maps, as I previously described, but rather than using just the true atrophy for each of the subject as training points, what we do is that we simulate a range of possible atrophy maps and then sample a value for each region from a distribution of population atrophies. It is important to note that the aim here is to train the network to estimate displacement fields from any reasonable value of prescribed growth or atrophy, rather than learn the deformation patterns from the population. We evaluate the performance of the network on the test set by comparing the prescribed atrophy maps with the computed atrophy, and then comparing as well the final simulated images and the segmentations to the ground truth second time point images. We show minimal residuals between prescribed and computed atrophy and report high dice overlap for the ventricular region across all subjects, showing that the model can accurately simulate the deformation patterns in the ventricles, with larger errors being observed for the cortex region. When training the second part of the model, the atrophy estimator, we fix the weights of the pre-trained biomechanical model. As previously described, the goal of the atrophy estimator is to learn region-wise atrophy values from subject metadata. We use a simple 3-layer MLP that outputs a vector with 27 values, one for each region of the parcellations that we are considering, and taking as input the diagnosis, age, sex, and a certain time window that we are between the scans. We train this model using the metadata from the training set and corresponding true image pairs, and use similarity metrics between the deformed image and the ground truth follow-up scans as the loss to train the model. We evaluate the full model by comparing again the simulated and ground truth images on the test set, but this time with using the estimated atrophy from the MLP. We report high dice overlap for regions such as the ventricles, white matter, and temporal cortex. In smaller regions, such as the hippocampus, we see slightly lower scores for some subjects, which might happen due to the larger regions being the driving force of the training, which is something that we aim to address in future work to improve this. Now, in order to evaluate the ability of our model to differentiate between healthy aging, MCI, and Alzheimer's, we use our trained MLP to estimate atrophy patterns for different classes. To do this, what we do is that we use metadata from the 105 subjects of the test set, but re-estimate the atrophy by intervening on the input channel corresponding to the diagnosis. We show that the model estimates statistically different values for different classes on ventricles and hippocampus. However, we do see that the model struggles to differentiate between MCIs and Alzheimer's when considering larger time spans. Now, this can be due to the lower number of training examples with AD with scans acquired for larger time spans, but also because MCI can convert to Alzheimer's diagnosis. And in this work, we are only considering the diagnosis that was given to each subject at the baseline. Now, if we look at the progression of atrophy for a specific subject, and if we compare the predicted atrophy for multiple time points for both the healthy and disease case, so here by intervening on the input channel of the MLP corresponding to the time span, and as well to the input corresponding to the disease, so here for cognitively normal and Alzheimer's disease. If we compare these trajectories, we can clearly visualize the difference in atrophy across the brain regions, including the ventricles and the hippocampus, which are here highlighted, which we know are influenced by Alzheimer's disease. So the results here shown show that the proposed framework can be used to simulate structural changes in brain shape resulting from neurodegenerative diseases, and we can differentiate between healthy and diseased atrophy patterns. It is important to note that in this work, atrophy was encoded to predict only demographic trends. We show that in this way, we can create a simple simulator of disease progression where one can easily intervene on one of these inputs, for example, the time or the disease class, and then both visualize and quantify the differences between classes. However, our goal is to expand the atrophy estimator network to better model the subject-specific heterogeneity, which we can't really model using just demographic data, by considering information that's present on the baseline image for each subject. So in the next stage of our work, we could use the regional atrophy that is estimated from the metadata as a prior, and then incorporate imaging information. So not only to improve the accuracy of the estimated atrophy values, but also to move from region-wise constant values of atrophy per region, which is what we are doing here, to then move to voxel-wise atrophy maps that can consider the subject-specific heterogeneity and better model the true atrophy patterns in the population. Thank you for your attention. I look forward to answer any questions that you may have.